Okay, this is a video on Introduction to Laplace Transforms, which is a great method for solving linear ODEs. Now, as a scientist or engineer, you might find Laplace transforms useful in the following manner. Suppose you have an RC circuit with the input x of t, resistor R, and a capacitor C. And let's suppose your output voltage was y of t. Now, using a little bit of math, you can turn this model into an ODE equation with the initial condition of, let's say, y of 0 is 0. From previous videos, you know that you can use the good old exponential guess method to solve for y of t. And when you do, you will be operating in the time domain regime of your problem. Now, this is all good, but sometimes this guess method is not possible. And the reason is x of t might be really complicated. So the purpose of a Laplace transform is to turn the ODE into an algebraic equation, where when you solve for y of s in the s domain, you're going to get just polynomials. So again, I'm going to draw a big box around this, and this is the s domain representation of your problem. And once you have y of s, you can use a lookup table to find y of t. Now this may be kind of a long way to solving this problem, but when x of t is really complicated, this method is really worth it. Well then, before we can talk about ODEs, we need to figure out what a Laplace transform actually is. So the bilateral Laplace transform of f of t is defined as the following. It's going to be the doubly infinity integral, so hence the term bilateral, of f of t times e to the minus st dt. Now when you evaluate this integral, you're only going to end up with a function of s. Now the first term here, e to the minus st, is called a kernel. Now you could think of this as a cousin of the good old exponential guess form e to the plus st. Now f of s is usually a polynomial where, you know what, in fact, it's usually a quotient of polynomials. S right here is a complex number, and it can be written in the form sigma plus j omega. We've seen this before, right? Now, to check out what a Laplace transform actually is, let's just check out an example. So suppose we were trying to find a Laplace transform of something called this step function. This is uber important. I'm going to put like 3 or 4 stars on this. In fact, it's so important it has a reserved name. It's called u of t, and we're going to use this a lot in this class. Now it's defined as 0 if t is less than 0, and 1 if t is greater than or equal to 0. So let's check it out on the plot. So I'm going to plot f of t equals the step function, and prior to t equals 0, nothing happens. Now t equals 0 and beyond, you will actually have a little step right here, and it becomes 1. Now at t equals 0, you have basically a discontinuity. Okay, you know what? Let's check out the Laplace transform of this guy. Alright, so what we're going to do is we're going to cookie cut this guy out, paste it onto the new page, and let's just check out the integral. So the Laplace transform of f of t is given by the following. This is it's the doubly infinity integral of f of t, e to the minus st dt. Now this integral has 2 parts. So we're going to first write the left portion prior to t equals 0. So it's going to be 0 times e to the minus st, and we see that prior to t equals 0, this integral disappears. So now we're going to write the right hand portion, which is going to be 1 times e to the minus st dt. So anything after t equals 0, this integral, you know what, it might exist. It depends on the value of s. Okay, after some calculus, you're going to get the following. The improper integrand. And since this is an improper integral, you're going to have the limit of t approaching infinity, e to the minus st minus e to the second term. We're going to plug that in here, which is 0. And e to the 0 is 1. So now this simplifies to the limit as t approaches infinity, e to the minus st minus 1. Now this limit term in here, if s was actually sigma plus j omega, we can plug that into the limit, and we're going to get e to the minus sigma plus j omega t. That equals probably the exponential envelope times cosine and sine waves, right? Cool. So again, this is waves, and this part is the exponential envelope. Now, that means for the limit to exist, you probably want this exponential envelope to be a decreasing envelope in terms of time. So let's check that guy out right here. So if we would like to have an exponentially decreasing envelope like this for a finite limit. So that means this guy is e to the negative sigma t. And if we plot the real part of the complex number, we're going to get an exponentially damped cosine wave right there. Furthermore, if we plot the imaginary portion of this complex number, we're going to get an inverted damped sine wave right there. So hence, in this case, both of these waves are damped to 0 as t approaches infinity. Awesome. So what it really means is the following. To have a finite limit, this exponential term must have sigma as a positive number. Yes. Now furthermore, if s was sigma plus j omega, we know that sigma is just a real part of s, right? So we can rewrite that relationship as real of s is greater than 0. This is uber important. So this is the condition for a finite limit and the existence of the Laplace transform right there. So what we're going to do is we're going to cookie cut this guy out again and clean this page up. There you go. So we're now concerned with this limit. So this limit exists if the following happens. If s equals sigma plus j omega, and if the real part of s was positive, then this limit is actually 0. Cool. And then we have a vestige term minus 1. So hence the Laplace transform for the step function u of t is just 1 over s, with the region of convergence, or ROC, of real part of s is greater than 0. Awesome. Okay, so we can use similar integral methods to find Laplace transforms for other functions. So if we have the time domain and the s domain, if we have a function f of t, the Laplace transform is usually written as f of s. Now for the step function that we just saw, where there is a step from 0 to 1 when t equals 0, that Laplace transform was 1 over s. Now we can define a ramp function r of t that looks kind of similar, where nothing happens here. And on the right hand side we have sort of an escalator looking thing like you see in a shopping mall, and that line is just t. So if you do the integral, the Laplace transform is going to be 1 over s squared. Now you can find a parabolic function where the right hand side kind of now looks like a water slide at a water world. And if you do the integral, the Laplace transform is 1 over s cubed. There's something conspicuous here. And this guy and this guy, they're just derivatives of each other, right? How about this guy? They're also derivatives. Whoa. Does that mean in the s domain, when you multiply it by s, is just the same thing as taking the derivative in the time domain? Is it that simple? And you know what? The real answer is it's 90% that simple. So let's take a look. So we have the time domain and the s domain in our Laplace transforms toolbox. So f of t transforms into f of s. And it turns out that if you differentiate f of t, you're going to get an s multiplication, f of s, minus f of 0, where that term is actually the initial condition for f at t equals 0. So that came from the unilateral Laplace transform, so the integrals from 0 to infinity of the same integrand. Now, this we usually don't use in this course, and the reason is we're most likely going to be working with initial conditions where that term is 0. Okay, so to finish off, we've learned in this lesson that u of t, the step function, is 1 over s for Laplace transform. And if you check out the worked out examples, an exponentially decaying step function is actually 1 over s plus alpha, where you have an s shift in the s domain. Okay, so given these 4 facts, we are actually now ready to solve first order linear ODEs.